Hello students, today we will continue with next group, that is group 17. Group 17 is commonly called as halogens. Halo means salt producing. So these are actually salt producing substances. Whenever they react with metal, they produce salts, like they produce fluoride, chloride, bromide, iodide, etc. Group 17 elements include fluorine, chlorine, bromine, iodine and acetine. About them, acetine is a radioactive element and other elements are most commonly known like fluorine, chlorine, bromine and iodine. They have the general configuration Ns2Np5. So they require only one electron to complete the octet. And therefore they are very reactive elements. They are just neighbors to noble gases, and just like group 1 and group 2 elements, even group 17 elements, they show similarity among themselves. This property is not seen in other groups. We can observe a good variation or gradation in physical properties like melting point, boiling point, etc. So the main property of group 17 is that they are very reactive elements. Are found in seawater, and that's why it is called as rich source of halogens. Halogens, these are commonly indicated as X. X can be either fluorine, chlorine, bromine or iodine. Seawater contains chlorine, chloride, bromide, iodide of sodium, potassium, magnesium, calcium, etc. But we know NaCl is the main constituent of seawater. 2.5% by mass. This much sodium chloride is observed in seawater, and sodium chloride is obtained by evaporation of seawater. Some forms of marine life contain iodine in their system. So this is how halogens occur in the nature. Moving on to the properties of halogens. First one is electronic configuration. Just now we have seen the general electronic configuration is Ns2Np5. Requirement of only one electron to complete the octet makes it very reactive. The chemistry of bromine, iodine and acetine is very much affected due to presence of d and f orbital in them. The second property is atomic and ionic radii. As we move down the group, the atomic radii increases from fluorine to iodine, as you can see in this information. It is due to increase in number of shell. The increase from bromine to iodine is not that much great, and fluorine being exceptionally small, because it is a period of second, it is an element of second period, and therefore it will show exceptionally small size. Now overall, if we talk about the atomic and ionic radii of halogens, they are the smallest radii among the given period. For example, fluorine will be the smallest element of the second period. Chlorine will be the smallest element of the third period. So all the halogens have smallest atomic radii in their respective period. It is due to maximum effective nuclear charge in them. Effective nuclear charge increases, but the electrons are added in the same shell. Therefore, Z effective increases, and as a result, halogens become smallest in their respective period. The next trend is ionization enthalpy. Ionization enthalpy means tendency to gain electron. But halogens, since their outermost configuration is Ns2Np5, they require only one electron to complete the octet. Therefore, their ionization enthalpy is very high. They have very less tendency to gain electron. And again, as we move from fluorine to iodine, that is, as we move down the group, ionization enthalpy, it decreases. But mainly you have to remember that the ionization enthalpy of halogens, it is very high because they have tendency to gain the electron and not to lose. So as just now we have discussed, the IP of halogens is very high, but their electron gain enthalpy is maximum negative in their corresponding periods. Maximum negative electron gain enthalpy, that means they will easily accept the electron. This maximum negative electron gain enthalpy is basically due to, as I have told you, the configuration Ns2Np5, requirement of only one electron, and gaining of only one electron will give them stable noble gas configuration, and therefore their electron gain enthalpy is maximum negative. But here there is an exception to the rule that electron gain enthalpy becomes less negative down the group. So this exception is of fluorine and chlorine. Fluorine has comparatively less negative electron gain enthalpy as compared to that of chlorine. Actually, chlorine should have less electron gain enthalpy as compared to fluorine. That means chlorine will easily accept electron as compared to fluorine, but the case is reverse. Fluorine has less negative electron gain enthalpy. The reason lies in the configuration. Fluorine has configuration 2s to 2p5. So 2p orbital is comparatively small orbital. The added electron goes to this small 2p orbital. So what happens? Electron repulsion increases, and therefore electron gain enthalpy of fluorine is comparatively less negative. That means it will accept the electron with little bit difficulty as compared to chlorine. Chlorine, on the other hand, have the configuration 3s to 3p5. So the added electron goes to 3p, which is comparatively larger orbital. So electron repulsion will be comparatively less, and therefore electron gain enthalpy of chlorine is comparatively more negative. This is most frequently asked question in the board exam. So a give reason question where these key terms must be included in your answer. Next property is electronegativity. Halogens have very high electronegativity. The electronegativity decreases down the group. But all halogens, they are highly electronegative. Out of the all elements that we know in periodic table, fluorine is the most electronegative element of the periodic table. It will try to attract all the shared pair of electron towards itself. So fluorine is the first and strongest electronegative element, followed by oxygen, followed by nitrogen. Now these three we can remember as phone. So the key term to remember three most electronegative elements, phone. They will attract the shared pair of electron towards themselves in a bonded atom. So here becomes the important question that although fluorine is most electronegative element, still its electron gain enthalpy is less than that of chlorine. It is many a time repeated question. If we look at the physical properties of these elements, we found that fluorine, chlorine exist in gaseous state, bromine exists in liquid state, and iodine exists in the solid state. Bromine is the only non-metal that exists in the liquid state. Now, we have to remember one more interesting thing about the halogens. All halogens are colored substances. The reason behind this is the presence of unpaired electron. NH2-NP5 configuration. So unpaired electron is present. This unpaired electron, it will absorb color or it will absorb the radiation in the visible range. And this absorbed color, it will be emitted out again in the visible region. And therefore all the halogens are colored substances. This is your important give reason question. So all these halogens shows a specific color. For example, fluorine is yellow in color, chlorine is greenish blue, bromine is red in color, and iodine is violet. Regarding the solubility of these elements in water, fluorine and chlorine, instead of getting dissolved, they will react with water. Bromine and iodine, they are sparingly soluble in water, but they are readily soluble in chloroform, carbon tetrachloride, carbon disulfide, etc. So what are these? These are actually organic solvents. So we can say bromine and iodine, they are readily soluble in organic solvents. Melting point and boiling point of halogens increases with increase in atomic number. As the atomic number increases, the atomic mass also increases, the London dispersion forces increases, and therefore melting point and boiling point also increases. There is one anomaly in bond dissociation enthalpies of fluorine, chlorine, bromine and iodine. So from this table, we can note that the bond dissociation enthalpy of fluorine is less than that of chlorine, and then from chlorine onwards it follows the expected trend that chlorine bond dissociation enthalpy greater than that of bromine, greater than that of iodine. But there is anomaly or there is an exception in case of fluorine. The reason lies in the structure of fluorine. Fluorine being small in size, the lone pair, there are so many lone pairs, they lie close to each other. And therefore, lone pair repulsion is quite high. As a result, the bond dissociation enthalpy, that is low as compared to that of chlorine. In chlorine, what happens? In chlorine, the size is bigger. So lone pair, they lies little bit away from each other. So the repulsion reduces. And this is the reason why chlorine is highly reactive. So fluorine is the most reactive among all halogens. The reason, low bond dissociation enthalpy. So the bond gets broken very easily, and therefore all the reactions of fluorine, they are highly exothermic, as well as they are very difficult to control. They are violent reactions. Low bond dissociation enthalpy also explains the reason that fluorine is the strongest oxidizing agent. Since the bond gets broken very easily, it can lose electrons very easily. It will gain the electron very easily, and therefore fluorine is the strongest oxidizing agent. This is also asked as a reasoning question, that why fluorine acts as an oxidizing agent. So in today's video, we have seen the introduction part of the halogens, and we have discussed the physical properties and other properties of halogen. That's all for the day. Thanks for watching. Have a nice day.